Okay, so I want to find the internal normal shear and bending moment at point C for this beam here. Okay, and the way we do this is we treat it just like we did method of sections with trusses. Okay, so the first thing I'm going to do is I'm going to find the reactions. Okay, so I have AX, I have AY, and I have B like that. Okay, and then I'm going to separate this the triangular load into a single force. That's going to be, since it's a triangle, it's going to be 2 meters from the left because it's 1/3 of the 6 that I have there, and its area is 1/2 6 times 4, basically the base times the height there. Okay, which is going to be, is that 12? I think that's 12. Okay. Okay, so from this, basically, I find that AX equals 0. Not a big surprise. I can sum the forces in the y direction. I'll have AY plus B minus 12 equals 0. And I'll sum the moments about A. Okay, and I'll get 6 times B minus 2 times 12 equals 0. From that, I'll learn that B equals 4. And then AY equals 8. Okay, and I know AX equals 0. Now, from that, okay, now that I have those reactions, I can make my cut just like I did with the method of sections on a truss problem. Okay, and what I can do is I can break this up into 2 pieces, as shown here. Okay, so the left piece, I have AY acting on that, that's 8. Then I've got this distributed load, like so. Okay, which starts at 4, and then halfway down, okay, it'll just be at 2. Okay, because over on the other side, I have the exact same thing, picks up at 2 all the way down to the end. And again, I got that because I'm cutting it at the middle. So, with a straight line, it's just going to be at the middle there. Then at B, I have 4. Now, what I'm actually trying to find is this normal force, this shear force, and this bending moment. Okay, and that's the positive sign convention. Don't get too worked up on the signs, positives and negatives. We'll worry about that when we get to the next course in mechanics of materials. Okay, but you have this on both sides. Okay, so if it's to the right on the one side, the force has to be the left on the other, right? If it's down on one side, it's got to be up on the other. If it's counterclockwise on one, it has to be clockwise on the other. Okay, so again, following Newton's third law. So I've got these 2 pieces here. Okay, and again, this is just like we did with the trusses, except with the trusses, I only had a normal force, right? It was either tension or compression. Here I've got some shear and I've got some bending moment. I still just need to draw one side. Okay, I'm going to deal with this one because I don't want to deal with the trapezoid. Triangle is going to be much easier than that. So with this guy, I'm going to sum the forces in the x direction. The only force I have in the x direction is that N. Okay, so I've learned that N equals 0. Kind of trivial there. In the y direction, I've got my V going straight up. I've got my 4 going straight up. And then I forgot to do this. I have to have my distributed load. Okay, it's going to be 1 meter away from the flat side, and it's going to have a magnitude of 1/2 3 times 2, which will be 3. So again, that's going to be, this is creating a negative moment. I don't care about the moment right now. It's just the shear force, or the vertical force, I should say. It's going to be down, and it's going to be 3, right? Because that's going to equal 3, and it's going straight down. So what the main thing to take away here is you have to redraw your distributed load. Don't just treat that 12 as now a point load. It's still a distributed load. Anytime you cut it, you have to redraw and redo that distributed load. Okay, so make sure that you do that when you do it. From that, I easily find that my shear force, my internal shear force, is -1, and all that negative sign means is that I drew my shear force in the wrong direction. You'd flip them, and you'd have to flip them on both sides if that's what you want to do. You still have to follow Newton's third law. So again, you make an assumption of the wrong direction, you just get a negative answer, and it's okay. Finding the moments. It's always best to sum the moments about the cut point. That way, N and V go away. You don't need to include them. What doesn't go away is the moment that I'm trying to find here. So make sure you include negative M because I've got that negative moment there. Then I've also got the negative 1 times 3. That's the triangular load, that distributed load that I've now redrawn my point load 1 over 3 down. Okay. And then I've got the reaction force at B, which is 3 meters over times 4. And that's going to be a positive. Set that equal to 0. And from that, I learned that my moment is 9 kilonewton meters. Okay. And the fact that I got a positive answer simply tells me that I drew my M in the proper direction. Okay. So again, don't worry necessarily about positive or negative. As long as you understand what direction it's going in, that's good enough for now. So you can draw them in whatever direction you want. Just make sure you follow Newton's third law, and that when you sum your forces and your moments, that you use the directions that you've drawn. And then just know if you get a negative answer, the opposite of what you assumed is true.